Here in this video, I will be teaching you about the concept and the derivatives related to Coulomb's law and all the numericals concerned this Coulomb's law I will be teaching in the coming video. So let's start with the concepts of Coulomb's law. Coulomb's law helps us to find the force between the 2-point charges. Now, what the key point here is that it always exists between the force exists between the 2-point charges. The name of the point charges I have explained earlier in my previous video. The concept of point charges, you may refer to that video. So here, now if we have two charges, that is one is Q1 and the other one is Q2 in a space or in vacuum, and they are separated by a distance r, then a force exists, that is a force of repulsion exists between these two like charges, and whose magnitude the Coulomb's law will help us to find it out. It states that the force is inversely proportional to the square of distance between these charges. It is directly proportional to the product of magnitude of the two charges, and it acts along the line joining the two charges. Now here, this statement is very important, that it always acts along the line joining the two charges. That means it always acts along this line. It never acts along this line. If we draw on this line, no, it is not. If we withdraw this particular line, no, again it is on this direction, it will not be acting. There is only one particular direction in which the Coulomb's force law will be acting. On combining these two factors, what we will get? F equals to K Q1 Q2 by R square. Where this? Because we have removed the proportionality sign, so we have to introduce one constant of proportionality, which is K. Now the value of the K is 1 upon 4 pi epsilon naught. So the formula for F becomes 1 upon 4 pi epsilon naught Q1 Q2 by R square. Now we will be learning more about this constant of proportionality, that is 1 upon 4 pi epsilon naught. In air, in SI unit, the SI unit of K is equals to 9 into 10 to the power 9 Newton meter square per Coulomb square. Now, here one symbol we are finding epsilon naught. This epsilon naught signifies the permittivity of a medium. Now, this is a new word. Throughout the unit 1, we will be referring to epsilon naught, epsilon, epsilon r. All these are the permittivities. So, let us first begin with the introduction of this word, that is permittivity. Permittivity is the property of the medium which determines the electric force between two charges situated in the medium. Minded, it is that property which determines whether the force between the two charges is going to be the very strong or very weak. That is called as the permittivity. So, if the charges are present in a medium, the force between them is going to be a weaker one, or it could be a stronger one. That is the deciding factor, is called as the permittivity. Now, I hope the meaning of this epsilon naught might be clear to you. If the charges are present in any other medium, then we have the epsilon. So, the force between the two charges may vary. It depends on medium to medium. The SI unit of epsilon is this much Coulomb square per Newton per meter square. See here, the unit of epsilon naught and the unit of K, they are reciprocal to each other. So, it is very easy to remember these units. So, please remember the values and the units, as that can be asked in the exams. Its dimensional formula is this one. This can also be asked as a 1-mark question. So, please go for it. Now, next, another very important thing, in CGS system. CGS means centimeter unit system. The value of K becomes 1. So, in CGS, the formula for the Coulomb's force becomes Q1 Q2 by R square. There is no constant of proportionality because its value is going to be 1. So, all the important concepts related to Coulomb's law I have explained you. You will write all these concepts. You are going to get full marks in the exam. Don't miss to write all the statements. Next, the topic is unit of charge. In the previous video, I have explained about the electric charges in detail. So, there what we have learnt is that as a unit of charge is Coulomb. Now, in this video, we will define the Coulomb. What is 1 Coulomb of charge? So, for that, in the equation, basic equation, what we have, F equals to 1 upon 4 pi epsilon naught Q1 Q2 by R square. In this equation, if you are going to put the value of charges Q1 Q2 as 1 Coulomb and the distance as 1 meter, so this particular term is going to become equals to the 1. So, what we are left with is F equals to 1 upon 4 pi epsilon naught 9 into 10 to the power 9 Newton. So, this is a constant value for the force when the two charges are of magnitude 1 Coulomb and are separated by a distance of 1 meter. So, based on this statement, we can have the definition of 1 Coulomb is, it is that amount of charge which repels an equal and similar charge with the force of 10 to the power 9 Newton when placed in vacuum at a distance of 1 meter from it. Mind it, here, there are certain keywords. What are they? The charges must be present in vacuum. They must be at a distance of 1 meter. The magnitude of charge should be the 1 Coulomb. So, there will be a force of attraction or repulsion between them of magnitude 9 into 10 to the power 9 Newton. So, if you can give this particular definition. Now in CGS, the unit of charge is ESU, that is called as electrostatic unit, or it is called as the stat coulomb. Now based on this, we can again define the one ESU of a charge. It is that charge which repels an identical charge in vacuum at a distance of 1 centimeter from it with a force of 1 dyne. So in this definition, these two are the keywords. There you have to just change the unit of the parameters. What are they? The two charges must be at a distance of held at a distance of 1 centimeter, and the force between them will become 1 dyne. Then the magnitude of the charge is equals to the 1 coulomb, where 1 coulomb is equals to 3 into 10 to the power 9 stat coulomb. This is the relation between SI and CGS system of unit. So please go for it. This is again another important key point or a concept related to the the Coulomb's law. Next, we have the Coulomb's law in vector form. Now, in vector form, we know that vector is a quantity which is having both magnitude and direction. So, when we are dealing with force, so the direction of force is important. So, in this article, we will be concentrating on the direction of force. Whenever we have the two charges, suppose Q1 and plus Q2, so there the force acting on these two charges will be what? So where various terms that we will be having is F21 and R21. What is F21? F21 is the force on this second charge because of the presence of first charge. Now this first charge will be repelling this Q2, so the direction of this F21 will be in this direction. And R12, what is R12? R12 is the unit vector pointing from Q1 to Q2. If we start moving from Q1 towards Q2, what we will find that we are moving in a direction of R12 position vector. That means the direction of F21 and the direction of F12 are same. So we can have the formula for F21 as 1 upon 4 pi epsilon naught Q1 Q2 by R square. Minded, here this is the magnitude part only. Now since we are dealing in a vector form, so if this side is having a particular direction with the direction of F21, in that direction we are having a position unit vector, that is R12. Here this R12 and F21, they are pointing in the same direction. So this is our balanced equation in the vector form, where R12, that is unit vector, can be represented as vector R upon its magnitude. Next we have F12. What is F12? It is the force on first charge due to second charge. Mind it, here this is the first charge and this is the second charge. They are of similar nature, so naturally they will start repelling. So this is the direction of F12 in this direction, F12, and in this direction what is the position vector? The position vector is that when we are moving from Q2 towards Q1, that is, it is having the direction of R21, which is the unit vector pointing from Q2 to Q1. So what our formula will become? Formula for F12 will become this magnitude part and to R21. So here F12 and R21, they are pointing in the same direction. So this is the formula, and one basic formula we have for F21. Now in the diagram, what we are finding is that the position vector R12 and position vector R21, they are opposite to each other. So we can write unit vector R12 is negative of R21. So now here in this formula of F12, if I replace this R21 with minus of R12. See here minus, because here I am replacing R21 with the sign of minus of R12. Now here what we are having R12, that means it becomes the formula for F21. So F12 is nothing but it is equals to negative of F21, that is force on second due to the first charge. This is how we have derived the Coulomb's law in vector form. I have given all the necessary steps to write this particular derivation, so please go for it. And the important consequence of this Coulomb's law in vector form is that Coulomb's law obeys Newton's third law. This particular statement says that for every force there is equal and opposite force. So it confirms the Newton's third law. That means Coulomb's law in vector form obey the Newton's third law. An important part, F12, that is force on 1, is plus the force on second charge must be equal to 0. Sum of the forces in a particular system will always be the 0. So here these are all the necessary steps for the derivation of Coulomb's law in vector form. In exam, if you will write, you are going to get the full marks. Next we have the concept check. Now let us see. The general question that can be asked in the exam is general question, the repulsive Coulombian force. That is, it is for Q1 is Q2 is always greater than 0. How we can represent this repulsive Coulombian force? If we have the two like charges, that is two negative charges. This one is the negative charge and this one is also a negative charge. So this is the direction where the repulsive forces will be present. So Similarly, we have another like charges, that is two positive charges. So repulsive Coulombian forces will always point opposite to each other. This is how, and Q1, Q2, the product of Q1, Q2 will always be greater than 0. Here see, if we have two minus negative charges, here see, if we have two negative charges, this negative charges, and here this negative charges, negative into negative will become again positive, that is it will be greater than 0. And if we have two positive charges, two positive, product of positive charges will become greater than 0. So if this situation is asked, what is the significance of Q1, Q2 is greater than 0? That means we are having the system of two like charges. This is the one concept. Next, we have attractive Coulombian forces. For that, Q1, Q2 must be less than 0. Now, attractive Coulombian force means the force must be attractive in nature. Now, when this force will be attractive in nature? When we have the two unlike charges. That is, if one is negative charge and the other one is positive charge. So here what we are finding, the Coulombian forces pointing towards each other, that is, this is attractive in nature. So whenever it is asked if Q1, Q2 is less than 0, that means it signifies that one of the charge we are dealing is negative and the other charge has to be the positive. Then only this product will give us the attractive Coulombian force. So this is an important concept check related to the Coulomb's law. When the Coulomb's force are repulsive, so with which type of the charges we are dealing, and when the Coulombian force is attractive, with which type of the charges we are dealing. So please keep this in mind. Next is limitations of Coulomb's law. So all the important derivations related to Coulomb's law we have learned. Now there is one limitations. You might be reasoning that it is valid in all situations, but it is not at all. It is valid only under the following condition. Let us see. Whenever the electric charges must be at rest. So this is again a keyword. When the charges are at, then only the Coulomb force exists between these two charges. When the same charges are in motion, then this force, this law is not at all valid. Next is the electric charge must be the point charges. Again here the term point charges is coming, whose meaning is that the dimension of charges must be much smaller than the separation between them. So that is why the Coulomb's law is valid only in case of the point charges. Next we have the separation between the charges must be greater than the nuclear size. That means within the dimensions of nuclear size, the Coulomb's law has no application, because there the nuclear forces dominates over the Coulombian forces. So these are the three cases, three conditions under which the Coulomb's law is valid. Now next is dielectric constant or relative permittivity, another very important topic. Now see, first of all, what is permittivity? So permittivity is the property of a medium which determines the electric force between two charges situated in that medium. In the previous article, we have learnt that whenever two charges are placed, there is a force between them. But now here we will be concerning about the medium in which these two charges are being placed. So what is the role of the medium? With the help of an example, we can find is that the force between two charges located some distance apart in water is about 1/80th of the force between them when they are separated by the same distance in air. What does this statement mean is that, suppose if we are having the two charges Q1 and Q2 that are present in air separated by a certain distance, so naturally a magnitude F, force of F will be present in between these two charges. But when the same two charges are present in a medium, let us suppose the medium becomes water, the magnitude of charges are same, the separation between them is again be the same, everything is same, only the thing is that we have changed the medium, which is water. So now whatever the force is acting between them in water will be 1/80th time that the force which was present earlier between them when they were in air. That means the force is reduced. That means whenever the charges are placed in a medium, the force will be reduced. Now here what I am referring is certain table, a relative permittivity of certain mediums. The first medium is vacuum, whose value is 1. Air we have 1.00054 and in water we have 80. So see here, the medium which is having that much greater electric constant, that much force will be reduced by that much. That is more the relative permittivity, lesser will be the force. That means these two charges will be interacting with the very lesser magnitude in a medium, whereas in air they are interacting with the greatest magnitude. That is what is the concept of relative permittivity is all about. So why the force in the medium is reduced? The force in a medium is reduced because the absolute permittivity of water is about 80 times greater than the absolute permittivity of free space. Here you can find is that the permittivity of water is 80 times that in the vacuum. So more is the relative permittivity, the lesser will be the force present between them. Lesser is the permittivity, more or the strong force will be present between the two charges. This is the concept of the permittivity. So directly in indirect sense, it gives us the magnitude of the force, how the force is going to be affected when the charges are present in different media. Now, let us find one formula related to this. Whenever the force is present between the two charges in vacuum, we are having a formula F vacuum is equals to 1 upon 4 pi epsilon naught. Here we are dealing with pi epsilon naught and Q1 Q2 by R square. But when the same charges are present in any medium, what the formula will be? F medium. See here, we have to write F medium, which becomes 1 upon 4 pi epsilon. Here the difference is that we are not writing epsilon naught because epsilon naught is the permittivity of a free space or a vacuum, whereas epsilon is called as the permittivity of the intervening medium. It is called as the permittivity. Yani ki this epsilon is the deciding factor which will decide what will be the magnitude of the force between the same two charges which were there in a vacuum. So what is the effect of this medium? If we will divide these two forces, that is force in vacuum and force in medium, the ratio of these two forces, we will get the ratio of epsilon upon epsilon naught, and this ratio is called as the relative permittivity, which is equals to epsilon upon epsilon naught. So this is also equals to ratio of F vacuum to the F medium. So the definition of relative permittivity, it is the ratio of force between two charges placed some distance apart in free space, ratio of force in free space to the force between the same 2-point charges when they are placed same distance apart in a given medium. So it is the ratio of two forces. So another important concept related to this relative permittivity is that it is a dimensionless and a unitless quantity. Keep in mind, for epsilon naught we have defined the unit in the previous article. In this video only I have given you the unit and the value of epsilon naught, but here for the relative permittivity it is unitless and a dimensionless quantity. It will be having only a magnitude part. So the important concept always what you will find whenever the same two charges are placed in a medium or whether they are placed in a vacuum, the force present between them in a medium will always be less than the force between the same two charges when they are present in the vacuum. That means in vacuum the charges experience the greatest amount of force, and in any other medium the magnitude of the force always decreases. Have you ever wondered how other electric charges will interact if they pass nearby an object with a known amount of net charge? That means if in a space huge amount of charge is present on a body, what will be its effect on other smaller bodies which are placed near to it? In order to understand this statement clearly or in detail, you must know the concept of the electric field. Now, in order to understand the concept, let us imagine a situation where we are having a charged body plus Q in the space called as the source charge, and another test charge having a small charge on it called as the test charge body, denoted by the Q naught. It is initially free to move in a space because it is not under the influence of this plus Q source charge. Now, whenever we place a source charge in a space, the region around it gets modified because of its present, and this modification we have shown by the electric field lines, that they are the imaginary field lines. Whenever the test charge will come under near this source charge, it will experience a kind of a force that is because of the presence of the electric field. Here lies the concept of the electric field. Now, so let us understand the another situation where we are having the same source charge which is present in the space. Here we have the same source charge, but this time a test charge is placed near to the source charge. So now it will experience a kind of a force. Now from where does this force come? This is because of the presence of the electric field around the source charge. This electric field will exert a kind of a force on the test charge, and this is all about the concept of electric field. That means it helps us to find out the magnitude of the force experienced by the other smaller bodies. Now next we have the concept of the electric field. Now let us begin with our important topic, that is its definition and what are the important steps in its derivation. So what we are having, first definition. How we can define it? It is defined as the electrostatic force per unit test charge acting on a vanishingly small positive test charge. As I have shown you, if we are having a source charge plus Q placed in a space, the region around it gets modified by the presence of the electric field. Now, if a test charge is placed near to the source charge, it will experience a kind of a force. Now mind it here, the test charge have to be the vanishingly small. Why is it so? That is how we can represent it. We can represent it as a limiting case of Q naught is tending to 0. This is the very important part in defining the electric field. So what will be the definition? It is defined as the limiting case where Q naught is tending to 0 force per unit test charge. Now I will explain why we should need a vanishingly small positive test charge. But before that, let's go for the electric field. Here E is a vector quantity. Why? Because its direction is same as that of the force F experienced on a positive test charge. If we are having a test charge is placed, just a minute, let me erase. So now if we are having a test charge placed in this at this point, so it will experience a force in this direction. If we place the test charge at this point, it will experience a force in this direction. Or if we place a test charge in this direction, it will experience a force. So whatever, depending on the position of the point charge, the direction of force keeps on changing, and hence the direction of electric field keeps on changing. That is why we call it as a vector quantity. That means its direction is same as that of the force experienced by the test charge. Now there is one concept check. What it has to say for us? That means the test charge Q naught, it may disturb the charge distribution of the source charge, and hence it may change the electric field which we want to measure. If we take this Q naught to be of measurable quantity, that means if it is of a certain big amount of quantity, 1 coulomb, 2 coulomb or certain microcoulombs, that means its presence can affect the presence of the field lines of the source charge, which we do not want. That is why in the definition we have defined Q naught is tending to 0. We cannot take the value of Q naught exactly 0, but it is tending to 0, 0.000 something coulombs. Value should be 0.00 in millicoulombs. That means the test charge Q naught must be small enough. Why? So that it does not change the value of E. So if in definition, if you give this point, it will be wrong statement. In definition, you have to give only this much statement in limiting case. Next, we are having units and dimensions of electric field. What are the units? First of all, as it is, electric field is defined as the force experienced per unit test charge. That means the unit of force is Newton, and for charge we have Coulomb, so Newton per Coulomb, or it is also called as volt per meter. Now for the dimensions of electric field, as electric field is the force per, electric field is force per charge. That means mLT minus 2. It is the dimensional formula of force, and Coulomb is the dimensional formula of test charge. So on solving this, we will get mLT minus 3A minus 1 will be its dimensional formula. Next, let us try to understand the physical significance of the electric field. As I have shown, the electric field lines are shown by this cases if we are having a plus Q source charge. That means the force experienced by the test charge Q naught is different at different points. So E also varies from point to point. As I have explained, if Q naught, the position of Q naught keeps on changing, so the direction or the value magnitude of electric field also keeps on changing. That is the important factor. So what we can say that E is not a single vector but a set of infinite vectors. So many vector directions are associated with the electric field. So we can say it is a set of infinite vector, not a particular direction. In a particular situation, it is having particular direction, but in a lump sum quantity, we will say we can have all the possible directions. So electric field is an example of a vector field. Next, by knowing the electric field at a point, we can determine the force on a charge placed at that point. So in spite of not using the Coulomb's law, we can also find the force in terms of the electric field. So this is its physical significance. It helps us to find the force experienced by a charge placed near a source charge. Now there is one key point. What is that? The electric field is the characteristic of a system of charges. That means this electric field is the characteristic of the source charge, not of the test charge. So mind it here carefully. Electric field is the characteristic property associated with the source charge or a system of charges. It is independent of the test charge. A test charge has no significance in its formulation. That is the important key point. Next, we will go for the derivation, the steps that you will be writing in exams, or whenever it is any question related to this concept is asked. If you will follow these steps, you are going to get the full marks. Let's see what are the steps. We are first finding the electric field due to a point charge. For that, let us imagine a situation where we have placed a point charge called as the source charge at the point O. Now at a point P, we want to find its effect, that is what will be the electric field intensity at the point P. So we have to place a test charge of vanishingly small magnitude at the point P. Now naturally this Q naught will experience a force in this direction. Why? Because they are of the similar nature. So it will experience a force in this direction. Now the separation between the Q and Q naught is R. Now, what will be the Coulomb's force experienced between this Q and Q naught? Already earlier we know already that it is 1 upon 4 pi epsilon naught Q naught by R square, and this is the unit vector R, which is pointing from O to P. Now, according to the definition of the electric field, what is that? Electric field is E equals to F upon Q naught. So, if you divide this equation by Q naught, so this Q naught and Q naught gets cancelled out. That is why in my previous article I have told you that electric field is independent of Q naught. It has nothing to do with Q naught. It is the characteristic property of Q only. So what magnitude wise in formula we will get for the derivation is 1 upon 4 pi epsilon naught Q by R square and unit vector R, that is it is pointing in this direction. That is, it is just a characteristic of the source charge. It has nothing to do with the test charge. So what will be the final magnitude wise if you want to write? It is simply equals to K Q by R square. That means it varies inversely with the R square. Next, we will try to understand the certain key points. What are the key points? As we have seen that the electric field varies inversely as R square. That means at all points on the spherical surface drawn around the point charge, the magnitude of E is same. That means if we will have a spherical surface, if we will draw a spherical surface like this around a source charge, at all the points on this spherical surface, the magnitude of E is going to be the same. That is called as the, and it is independent of direction of R, and this is called as the spherically symmetric or a radial field. That is the most important point. Why the electric field is a radial field or a spherically symmetric? Because at all the points on the spherical surface drawn around the point charge, the magnitude of E is same. That is why it is called as the spherically symmetric. Now, what is the importance of the electric field? Now, by this time you might have understood that electric field is a measurable effect generated by any charged object. It is called as the measurable effect generated. Next, in order to understand the nature of action at a distance force, so nature of action of the force, whether the force will be repulsive or attractive, the concept of electric field helps us to determine that. Now, next we are having the electric field lines, how we can represent the electric field lines. In case of a positive source charge, the electric field lines always point away from it. Always keep this in mind, they will always point away from it, because the test charge that we have taken Q naught, it is positive in nature. So naturally a repulsive force will be acting on the test charge, so electric field lines will be pointing away from the source charge. But if we are having a source charge as negative and we are having a positive test charge, mind it, here we have taken a test charge as a positive, so there will be an attractive force acting on this test charge, so electric field lines will always be pointing towards the negative source charge. Keep this in mind. For a negative source charge, the electric field lines are towards it. Now we are having one knowledge test. Let's see what the knowledge tests have. So here are some questions that are related to this topic that can be asked in board exams. If you have understood it well and write all the steps that I have explained, you will get the full marks. So go for these questions and present your answer very well. All the necessary steps which are required to explain the answers of these questions, I have already explained. Now let's go for some numericals. Before we go for the numericals, we have a quick recap. What I have taught in my previous videos, I have taught you about the concept tips on Coulomb's law. I have already dealt with the concept tips on superposition principle and numerical tips on Coulomb's law and superposition principle, which is very, very important. Please go for them also. You can get lots of knowledge from it. Now, let's start with some numericals. Here we go with our first numerical. Let's see, the 2-point charges +1 microcoulomb and +4 microcoulomb are kept 30 centimeter apart. How far from +1 microcoulomb charge on the line joining the two charges will the net electric field be 0? How to depict the given situation in the form of a figure? Let's see, we have placed the one charge Q1 which is +1 microcoulomb at the point A, the other charge Q2 at the point B. These A and B are separated at a distance of 30 centimeter. Now let us suppose P be the point where the net electric field is 0. Now at the point P, we want to compute the directions of electric field E1 and E2, which are due to Q1 and Q2 respectively. Let us see first E1, it is due to the Q1. Now Q1 is positively charged, so at the point P, The electric field due to the Q1 will always be pointing away from the positive charge. That is, its direction will be this one. Similarly, if we go for the direction of E2, E2 is due to the plus 4 Q microcoulomb, plus 4 microcoulomb. So it is due to again positive charge. So at the point P, the direction of E2 will be pointing away from the charge Q2. That is, E1 and E2, they are pointing in opposite direction at the point P. So diagrammatically we have shown them in the sense of direction. We have shown that E1 and E2. Now we can find the magnitude of E1 and E2. Further, let us suppose the point P is at a distance of x from the point A, and the remaining distance, that is the distance between P and Q2, will become 0.30 minus x, where we have converted it into meters. Now next, what we can have, the electric field at the point P will be 0 when we have E1 equals to E2, as they are pointing in opposite direction. Now the formula for E, already we know that it is KQ by R square. So if we will put this formula for our particular situation, what we will get? E1. Let us see E1 K, that is 1 upon 4 pi epsilon naught. E1 is due to the plus 1 microcoulomb. So here we have converted into coulomb as 10 to the power minus 6 coulomb upon R square, that is the separation between A and P is x. So we have taken x square. Similarly, if we want to find the value of E2, same magnitude. So 1 upon 4 pi epsilon naught. Here E2 is due to the plus 4 microcoulomb. So we have converted it as 4 into 10 to the power minus 6 coulomb upon the separation between P and Q2. It is 0.30 minus x whole square. Now on cancelling the certain like terms, we will get the next step. The next step will be this step, and on solving this we will get this value. If we will solve this equation, what we will get? X equals to 0.10 meter, that is 10 centimeter to the right of plus 1 microcoulomb charge. That means from the point A, if we have the 10 centimeter of distance, there the net electric field will become equals to the 0. This is how you can solve the numericals based on electric field. Now next, go for the next numerical. The 2 point charges plus 16 microcoulomb and minus 9 microcoulomb are placed 8 centimeter apart in air. Determine the position at which resultant electric field is 0. That means how to depict it? If we place 16 plus 16 microcoulomb at the point A, this is Q1. Q2, which is minus 9 microcoulomb at the point B. The A and B, they are separated at a distance of 8 centimeter in air, and P is the point where the net electric field we want to compute to be the 0. Now our first target should be to find the direction of E1 and E2. Now since E1 is due to Q1 charge, which is positive, so always in this direction it will be pointing away from the positive charge. So at the point P, this is the direction of E1. Now E2 is the electric field due to the Q2, which is negative charge. So its direction will be always towards the negative charge. So that is why at the point P, the direction of E2 is towards Q2. Direction of E1 is away from Q1. Keep this in mind. And now these E1 and E2, they are pointing in the same direction. Now further, let us assume that the point P is at a distance of x centimeter from the point A. So the remaining distance between P and Q2 will become 8 minus of x. Now we want to find it magnitude wise. What we can have, if P is the point where the net field is 0, so what we can have at the point P, we have E1 plus E2 equals to the 0. Why? Because E1 and E2, they are pointing in the same direction. So when they will add up, then only they will give us the net electric field as 0. Now again, the magnitude of E is equals to KQ by R square. So on putting the magnitudes, K is there. Now this E1 is due to Q1, which is plus 16 microcoulomb. So here we have converted into coulomb as 10 to the power minus 6 upon separation is x minus 10 to the power minus 2. Why we have included? Because we have converted centimeter into meter. Similarly, E2 is due to minus 9 microcoulomb. So here we have converted it as minus 9 into 10 to the power 6 coulomb, and the separation is 8 minus x, and we have converted into meters, and this is whole square equals to 0. On solving this and cancelling the like terms, we will get this step. Further, if we will cancel the steps, we will get this equation, and now the value of x comes out to be the 32 by 7 or 32 centimeter. Two values we will get for x, because we are having plus minus sign. Now if we see the situation, x equals to 32.7, that means x comes out to be the somewhere between 4 point something value. That means it lies between A to B. Now in between A to B, what we are finding, if we have a point P where electric field is to be the 0, it can never be 0. Why? Because E1 and E2 in between A and B will always be pointing in the same direction. So this particular situation we have to neglect, where the net electric field can never become 0 in between A and B. Now next, how can we find the other point? Now let us, the remaining point is x equals to 32 centimeter from A. That means if we move from A towards 32 centimeter, that is towards the right of Q2. That means in this somewhere over here. towards the right of Q2, there E1 and E2 will be pointing with their, see here, E1 will be pointing in this direction towards the right and E2 will be pointing opposite to E1. So this is the point P where E1 and E2 can cancel each other and the net electric field will be the 0. So mind it, when we are having the two unlike charges, that is one is positive and negative, so the net electric field will be 0 always on the other side of the charge. That is, it will never be in between the two charges. So at x equals to 32 centimeter, the electric field will always be the 0. This key point you have to keep always in mind. In between A and B, the net electric field can never be 0. Next, go for the next question. Now we have 2 point charges plus 6q and minus 8q are placed at the vertices B and C of an equilateral triangle ABC of side A. Obtain the expression for the magnitude resultant electric field at the vertex A due to these two charges. So this is the given figure. ABC is an equilateral triangle where at the point B we have placed a plus 6q charge and at the point C we have placed minus 8q charge. Now our aim, this equilateral triangle is of side, each of side A. Now our aim is to find the net electric field at the vertex A. So how we can find it out? Now at the vertex A, this plus q charge will be exerting a force or the electric field in this direction because it is positive. So this is EBA. It is denoted by EBA, electric field pointing from B to A, which will be pointing away from the plus q charge. Now next we want to find the electric field due to this negative charge which is at the C. So negative charge at the point A will take the electric field towards itself. So electric field at the point A will be pointing towards the negative charge. So this is the direction EAC, that is electric field pointing from A to C, it will be in this direction. Now diagrammatically or direction wise we have represented the electric field B and electric field C. Now what will be the resultant electric field at the point B? It will be the vector addition of EBA and EAC. Now let us see what will be the vector addition. How we can compute? Here the magnitudes of EBA. Now the general formula for electric field is KQ by R square again. So here this EBA, it is due to the plus Q charge. So here we have to put Q as 6Q and the separation between the A and B is A. So that is A square, that comes out to be the 6E. Now here for simplicity we have substituted E as a general formula 1 upon 4 pi epsilon Q by A square. So this Q by A square complete part we have substituted as E. So our EBA becomes 6 of E. Next we want to find EAC. Now what is EAC? EAC is due to the minus 8q charge. So here we have to put the magnitude of 8q upon A square, that comes out to be the 8E, where E is equals to 1 upon 4 pi epsilon Q by A square. So 8 into E we will get EAC. Here we are not putting the magnitude that is negative charge, here only we are keeping the magnitude part. Now let us see what will be the net electric field. The net electric field at this point will be always equals to the, here the net electric field is the vectorially we have to add. So what will be the vector addition of EBA and EAC? It will be the under root of EBA square plus EAC square plus twice of EAB EAC cos 120 degree. Now let us put the value 6E, 8E and cos 120 degree is minus 1 by 2. On solving this value we will get the formula for E net as equals to the E net equals to the E root 52, and now we will put the value of E as 1 upon 4 pi epsilon naught Q by A square. So this complete part becomes the magnitude of net electric field at the vertex A of an equilateral triangle. So here certain key points that you have to keep in mind is that vectorially you have to add these two electric fields because this is a vector quantity and the angle between them matters a lot. So we have to put the value. Next, go for the other question. 4 charges plus Q, minus Q and minus Q are placed respectively at the 4 corners A, B, C and D of a square of side A. This time it is a question based on a square. Calculate the electric field at the center of the square. Now let us see how we can depict the given situation. Here A, B, C, D are placed at the corners of a square. Now plus Q and plus Q are placed at A and B respectively. Similarly, minus Q and minus Q are placed at D and C respectively. I think this will be clear to you. Now, at O is the center of this square where we want to compute the net electric field. Now, let us see step by step. First of all, we will take the plus Q charge at the point A will exert an electric field in this direction. Why? Because it is a positive charge. The electric field will be pointing away from the plus Q charge. So, this is the direction of EA. Keep this in mind. Similarly, the charge plus Q which is placed at B will exert an electric field EB. Again, it will be away from the, it will be pointing away from the plus Q. So, at the point O, we have to draw this. This is the direction of EB. Next, C. the direction due to EC, that is direction due to C minus Q charge. Now at C minus Q charge is placed, so the electric field due to a negative charge always points towards the negative charge. So this is the direction of EC. From O, EC will be pointing towards the negative charge. Keep this in mind. Similarly, at the point D, we have placed a negative charge. Again, ED, the electric field which is due to negative charge will be pointing towards the point D, that is towards the negative charge. So this is the direction of ED. I hope now the direction will become clear to all of you. Once again, I will show it to you. EA is in this direction away from plus Q because it is due to positive charge. Similarly, EB is pointing away from the plus Q because again it is due to positive charge. EC is towards the negative charge. It is in this direction. Similarly, ED is also towards the negative charge. So these four directions you have to keep in mind. Rest magnitude wise we can find the value of the electric field, since all the charges are of equal magnitude. Here the charges are of equal magnitude Q, 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 and they are at the same distance R from the center. Now see here, the distance of O with respect to A, with respect to B, or with respect to C, or with respect to D, it is equal, which is equals to R. So this R distance we have to compute. Now here it is already given that the side of a square is A and here the side of the square is A. So how we can find the value of this R? This R we can compute it in the form of using the right angle triangle. Here if we are having a right angle triangle like this much, if they are at right angle, this is R and this is A. So what we can have, the magnitude of EA, EB and EC each will be equal, and that is equals to KQ by R square. Now the value of R using hypotenuse theorem we can get it as A by root 2. So now we will put the magnitude as KQ upon A by root 2 whole square. So that becomes 2 into KQ by A square. This is the magnitude of every magnetic field, that is EA, EB, EC and ED. The direction I have mentioned in the figure. Now let us see E1. Now we want to find the value of E1. Let me clear the figure first. Now E1. Now first we will find E1, which is the EA plus EC that is pointing in the same direction. So EA and EC, they are pointing in the same direction. So we will be having E1 is the net electric field. So magnitude wise we have to simply add up these values, that is EA is 2 into KQ by A square. Similarly 2 into KQ by A square. So on adding we will get 4 KQ by A square. Now next what we will be having, E2. What is E2? E2 is pointing in this direction. EB and ED, they are pointing. So we have to add these two electric fields. That is why we will get E2, which is EB plus ED. Again on the following the same line on the previous step, we will get E2 as 4 KQ by A square. So what is E1? E1 is the net of EA and EC. Similarly E2 is the net of EB and ED. Next, we want the net electric field. So the net electric field will be equals to the under root of E1 square plus E2 square. So now the sum of this and this will give you the net electric field. So magnitude wise we have to add up this value and this value. Ultimately it comes out to be, on solving this square or square root, we will get 4 into root 2 K Q by A square. So this. Now let's begin with the topic electric dipole in detail. To begin with, a dipole is a separation of opposite electrical charges. That is, an electric dipole occurs when positive and negative charges are separated from each other. And it is usually seen in molecules having a covalent bonds, for example, water molecules and HCl molecules. So here as you can see, we are having a negative charge and a positive charge separated by a certain finite distances. That will constitute an electric dipole. Next, we are having the dipole moment. A term which is associated with the electric dipole is a dipole moment. How we can define a dipole moment? That when the two charges are separated by a certain separation, that is 2a. So a physical quantity which is denoted by a symbol P, it is equals to Q into 2a, and it is always pointing from a negative to a positive charge. So about this physical quantity we will learn more about in this article. So now next we will begin with our topic, that is the electric dipole, its derivation and what are the key steps that we will be following. So as I have already told you that a pair of equal and opposite charges separated by a small distance. So here as in the diagram you can see we are having a negative charge and a positive charge. They are equal in magnitude but opposite in nature. They are separated by a separation that is 2a. O is the center. Now a physical quantity, that is dipole moment, will be pointing from negative to a positive charge. So this is how we can represent an electric dipole. So what is now the dipole moment associated? Certain key points related to dipole moment are, it measures the strength of an electric dipole. That means whether the dipole will be a very stronger or a very weaker one is decided by this dipole moment. Now further, it is a vector whose magnitude is either charge times the separation between the two charges, that is its magnitude is q into 2a, magnitude of either of the charge into the separation between them. And it's a vector whose direction is along the dipole axis from negative to the positive charge. That means it lies along the dipole axis. Now what will be the dipole axis? The axis which joins the center of the two charges will be the dipole axis, and it is always pointing from negative charge towards the positive charge. So you have to keep this in mind, and the SI unit of the dipole moment is Coulomb meter. Now next, what we will be finding is ideal dipole or a point dipole, a new term, that is an ideal dipole. What is an ideal dipole? A dipole whose size, that is 2a, is tending to 0. That means that we are having the two charges which are separated at an infinitesimally small separation. It is very negligibly small, but the magnitude of the charge is tending to infinity. That means the charges that we are placing, plus q and minus q charges, they are very greater in magnitude, in such a way that the net dipole moment should have a finite value. Further, the examples of an ideal dipole will be the dipoles associated with individual atoms or molecules. So this is all about your ideal dipole or a point dipole. Next, a very important term that is associated with dipole is a dipole field, about which we will be learning the derivation steps in more in detail. So let us first concentrate on dipole field. It is the electric field produced by an electric dipole, and see here we are having a dipole which is consisting of two equal and opposite charges. So the net total charge of an electric dipole is always 0, but still it will be having a certain dipole field. Why is it so? Because the charges plus q and minus q are separated by some distance, so the electric fields due to them when added do not exactly cancel out each other. Although the net sum of charge will be the 0, but these individual charges will be exerting some electric field at any of the point around the dipole. That means a dipole field is always associated with the dipole. So let's learn more about this dipole field. Let's start with an axial line. How we can represent an axial line? So it is the line joining the centers of the two charges. That means if we are having the plus q and minus q, the line which joins their centers will be called as an axial line, or any point which lies on this axial line will be called as an axial point. So here we will be finding the electric dipole. Next we are having an equatorial plane. What is an equatorial plane? If we are having the same charges plus q and minus q separated by certain distance, so a plane which lies perpendicular to the axial line at the center will be called as an equatorial plane, and any point which lies on this equatorial plane, or any point which lies on this equatorial plane will be called as an equatorial point. And one important point is that this equatorial point will always be equidistant from the either of the charges. It will this equatorial point will always be equidistant. So at equatorial point and an axial point, this dipole will be exerting an electric field, and our aim will be to compute that. So next what we are having, let us find an expression for the electric field at an axial point of a dipole. So for that, let us imagine a situation where we are having a pair of equal and opposite charges, that is minus q and plus q, are separated by a 2a distance. Now a point P is a point of observation where we want to compute the electric field due to these two charges, that is due to a dipole. Now see here very carefully that the plus q charge will exert an electric field at the point P, which will always be pointing away from the positive q charge, that is the direction of E positive is in this direction, that is along the positive x-axis. Similarly, the negative q charge will exert an electric field at the point P, which will always be pointing towards the negative charge. So the negative electric field, that is E negative, will be pointing along the negative x-axis. So these are the two electric fields which will be present on the at the point P. Now let us see, the point P is at a separation of r from the center of the dipole. Now we want to compute the net electric field at the point P due to the this dipole. This point P will be called as an axial point. So here first we will find the electric field due to a negative q charge at the point P. So what is the magnitude of the electric field? Electric field, we know that E equals to the kq by r square. So here k is 1 upon 4 pi epsilon naught. The charge value we have to put it as q. Its magnitude is only the q. We are not putting negative sign here. And the separation between the negative charge and the point of observation, you can see clearly here is
that it is R plus A, that is the separation of minus Q and O is A, and from O to P the remaining distances are, so the total distance of negative charge from the point of observation becomes R plus A. So this becomes R plus A whole square. Further, a vector, that is dipole moment, is associated which is pointing from negative to positive charge. So here we have to put a minus sign. Why? Because the direction of E negative is opposite to the direction of the dipole moment. That is why this negative sign has come over here. So this is the magnitude of the electric field due to a negative charge. Similarly, electric field due to a positive charge at the point P, that is at the point P, as electric E positive is pointing along the positive x-axis and the dipole moment is also pointing in the same direction. So here we are having a plus sign. So the magnitude becomes kq by r square, that is q upon 4 pi epsilon naught. Now the separation between plus q and point P will become obviously r minus of a. See here, only this much of the distance we want to calculate, so that will become r minus of a ka whole square, and it will be pointing in the positive x-axis. So the resultant electric field, at the point P will be the sum of E positive and E negative. So let us see, as they are there, what we will keep their magnitude. So q upon 4 pi epsilon naught. First we are putting this r minus a whole square minus of 1 upon r plus a whole square. Now if we will solve this bracket term, what we are going to get is r plus a whole square will be in the numerator minus r minus of a whole square upon what we will be having, r minus of a whole square into r plus a of whole square. If we will solve this terms, we will get this particular term, that is E axial will be pointing, the magnitude of the E axial will be 4ar. Now next, the total electric field, the net electric field E axial, if we will substitute from here, see here, physical quantity, that is P equals to Q into 2A. So from this expression, if we will take out 2A into Q, we are left with 2 into R. So we will substitute 2A into Q with P. So ultimate expression becomes 1 upon 4 pi epsilon 2PR upon R square minus A square whole square. And mind it, here E axial is pointing in the direction of the net dipole moment. It is coming with a positive sign. So next, what we will be having, the ultimate expression when we are considering that the separation, that is the point of observation, that is R, is very greater than the dipole separation, that is A. So in that case we can neglect this A square. So in the denominator part we are left with R to the power 4 and 1 RR cancels out. So 1 upon 4 pi epsilon of 2P by R cube. So this is the final expression for the electric field at an axial point of the dipole which acts along the dipole axis, that is from negative to positive charge, that is it is always in the direction of dipole moment P. This is one key factor that you have to keep in mind. E axial always points in the direction of the dipole moment wherever we have. One more important key point is that whenever you draw this diagram, always keep the plus Q charge at the right hand side and minus Q charge on the left hand side. If you will place it oppositely, that is if you will place plus Q over here and minus Q over here, so the expression or the terms will get cancels out. So here you will have the different denominator. So don't go for this type of the step while deriving. So these steps have been derived while keeping the plus Q charge nearer to the point P and minus Q charge far away from the point of observation. This is one key important point to be kept in mind. Now next, we are having electric field at an equatorial point of a dipole. As already I have explained what will be an equatorial point, a point which lies on the equatorial plane, which is perpendicular to the dipole axis and it passes through the center. So as you can see in the figure, what we are having, a dipole of minus Q and plus Q charge separated by a separation of 2A. Now P is the dipole moment which is pointing from minus Q charge to the plus Q charge, that is along the positive x-axis. Further, the point of observation P is at a distance of R from the center of the dipole. Always we have to take this distance of the point of observation from the center of the dipole. Further, this negative Q charge will exert an electric field which will always be pointing towards the negative Q charge. So here we have represented E negative, the direction of E negative. Further, positive Q charge will exert an electric field away from it, that is this will be the direction of E positive charge. So these two are the vectors and their equivalent is represented along this direction, that is E equatorial. Further, the separation of point of observation from either of the charge will be the under root of R square plus A square. From the Pythagoras theorem, applying in this right angle triangle, we will get this expression. Now we will find the magnitude of each of the electric field. What we can have, just see, Here we are having E positive will become KQ by R square. So 1 upon 4 pi epsilon naught Q by the separation between P and plus Q is under root of R square plus A square. So we have to remove the square. So ultimately we will get R square plus A square. Similarly, electric field due to a negative Q will become the same 1 upon 4 pi epsilon Q upon R square plus A square, because both positive charge and negative charge are at equal distance. They are equidistant from the point of observation P. So here we are, one key point is that although this is the electric field due to a negative charge, but here we have not placed a negative sign over here. We have to keep a positive sign here only. This is a very important key point. Generally the students do the mistake where they put the negative sign along with this, keep thinking that this electric field is due to the negative charge. So this mistake you need not to do that. Here this is the direction we have to take into consideration. Here we have taken only the magnitude of the charge. So by this what we are finding is that E positive and E negative, they are equal in magnitude. So here negative sign will not come. Further, what will be the resultant electric field at the point P? Now this is a very important step in its derivation. So here E equatorial, how we can get this final E equatorial? See here, E positive, in this diagram if you will notice, E positive is a vector. We can resolve it into its two component. One will be the E positive sin theta, which is pointing along the positive y-axis, and the other is E positive cos theta, which is pointing along the negative x-axis. So E positive, on resolving here we are having, this is the angle theta. So accordingly, E positive and E cos theta, they are perpendicular to each other. They are the components of this E positive net electric field E positive. So we have resolved. Similarly, E negative is again a vector. Resolving into its component part, one is E negative sin theta and another one is E negative cos theta. So their direction I have shown. So E negative sin theta is pointing in the negative y direction. Here we have seen that in this step we have seen that E positive and E negative, they are equal in magnitude, but here at the point P their sign component are pointing opposite to each other. So these sign components get cancel out each other, whereas E negative cos theta and E positive cos theta, that is their cos component, gets added up. So we are getting this expression E equatorial is the, now negative sign is introduced over here. E negative of E negative cos theta plus E positive cos theta. Now why we have introduced this negative sign? You can see here in the diagram, this dipole moment vector is pointing from negative to positive charge, that is along the positive x-axis, whereas E equatorial is pointing along the negative x-axis. So E equatorial and the dipole moment, they are pointing oppositely. That is why we have introduced the negative sign here. This is a very important factor. Here in E negative expression we have not put the negative charge. Here including when we are taking the sense of direction, then only we have included this negative charge. So this one is the one most important key point where the students generally do the mistake in substituting the sign. So I think I have cleared my point. So here E equatorial is negative of this much. So next we will on putting their magnitude, that means E negative and E positive, they are equal in magnitude. So what we are having, twice of E negative, E cos theta, and pointing in the dipole moment vector. Now our next step is to put their magnitudes value. What will be their magnitudes? Further, what we know that here minus 2 we have kept it as it is. Now E negative value we will put from this expression, that is 1 upon 4 pi epsilon naught Q by R square plus A square. Further, cos theta, if we want to find the value of cos theta from a triangle P minus Q and O, we will get cos theta as A upon under root of R square plus A square. So here we have to put the expression for cos theta. On further solving the like terms, we will get minus 1 upon 4 pi epsilon naught P upon, this one will become R square plus A square whole to the power of 3 by 2. So here you have to solve only the denominator part. Rest we have substituted this 2Q into A as P. Here one substitution what we have made, again dipole moment we have placed as 2Q into A. So the numerator part entirely we have replaced with the dipole moment. So what we are getting, this is the expression for E equatorial. Further, if we are having a condition where what we are having, if R is very greater than A, so neglecting this A term, we will get minus 1 upon 4 pi epsilon naught P by R cube. That is, electric field at any equatorial point of the dipole is anti-parallel to the dipole moment. This is the key factor because here negative sign is introduced. You can see E equatorial is pointing in negative x-axis, whereas dipole moment is pointing in positive x-axis. So these two are opposite to each other. That is why here the negative sign has been included. Now next what we are having, Comparison of electric fields of a short dipole at axial and equatorial points. So just now we have seen in the article that we can represent E axial by this expression and E equatorial by the negative of P by R cube. So if we will compare these two expressions, what we are going to get is that in E axial term only 2 factor, that is 2 factor is extra, rest of the thing is just we are having E equatorial. So E axial is equals to negative of twice of E equatorial, that is electric field of a short dipole at a distance of R along its axis is twice the electric field at the same distance along the equatorial line. That means if we are having a condition where the point of observation is at a distance of R at an axial line as well as it is at a distance of R at an equatorial point, so E axial will be equals to negative twice of the E equatorial. Now next we are having a knowledge test. So what we are having in knowledge test is that here we are having some questions that are based on these articles that can be asked in the boards. So every step I have explained, and if you will follow these steps, no one can deduct your marks and you can get a full marks in the exam. So present your answer well and go for each and every step. So now our next article will be torque acting on a dipole in a uniform electric field. It's a very important article. Now, a uniform electric field is represented by a set of parallel equidistant lines. So here we are represented the set of parallel equidistant lines as the E. Further, if we place a dipole which is having minus q charge and plus q charge at an angle of theta with respect to this electric field, so this is the force that will be now acting on the plus q charge, that will be equals to q into E. The force acting due to this external electric field will be q into E and it will be pointing away from the plus q charge. Similarly, the electric field will exert the charge force on the negative q charge which will be pointing in this direction, negative x-axis. So further, what will be the dipole moment of this dipole? It is equals to q into 2a. Further, the force exerted on the charge plus q by the field is qe, which is along the direction of the electric field, whereas force exerted on the charge negative q is minus qe, which is opposite to the electric field. That is why we have included the negative sign. If you will find that these two equal and opposite forces cancel out each other, but they constitute a torque. Now what will be the definition of the torque? It is the product of either force into the perpendicular distance between them. Now if you want to find the perpendicular distance between the positive charge and the negative charge, it is represented by this factor, that is 2a sine theta, where 2a is the separation between the two charges and theta is the angle at which the dipole is inclined with respect to the electric field. So what we have to put? The magnitude of the either force. So this q into E, we have magnitude only we have to put. So this we have taken it from this expression. Further, qe into 2a sine theta is the separation, perpendicular distance between the plus q charge and the minus q charge. On solving this, that is on substituting q into 2a with dipole moment p, we are getting pe sine theta. Since p and e both of them are vectors, so we can represent it as torque is equals to P cross E. So this is the final expression for the torque. Next. Okay. Next, there are the certain key points. What are the key points? When the dipole is released, the torque tends to align the dipole with the field. That is, it will always reduce the angle theta to 0. That means it tends to place the dipole along with the electric fields. And further, next important key point is when the dipole gets aligned with E, the torque becomes equals to the 0. That means if initially we are having a dipole is placed like this, this is minus q and plus q, and if it is placed in an external field, it will try to make its position like this much. Here, minus q should be on the left hand side and plus q should be on the right hand side, then only its dipole moment will be pointing along that electric field vector. So in this situation, torque will become equals to the 0. If you interchange the position of the charges, that angle between them becomes 180 degree. So in that case, you won't get the torque equals to 0. So you have to keep this in mind. How to place the dipole parallel to the electric field is that we have to align the dipole such that the negative charge is towards the left hand side and positive charge is always towards the right hand side. Then only in this situation torque will become equals to the 0. Further, we are having the torque on the dipole will be maximum when the dipole is placed perpendicular to the electric field. That means plus q is on the up and minus q on the downward negative axis. Then the angle between them becomes 90 degrees. So the dipole moment becomes maximum.